Welcome to the MEF 3.0 POC technical demo, Orchestrated Multi-Edge Clouds. In this POC, we would like to demonstrate two customer cases relying on edge computing technology. First of all, we assume that the customer wants to open a new warehouse branch with AI-driven smart sensors and a face recognition system. We will show how a DAS-based IoT service with SLAs enables the customer to reduce the opening time by utilizing CSP-provided applications and transport infrastructure. Next, we will move on to a migration scenario in which we focus on a manufacturing branch whose IT division foresees a new requirement for a network with higher capacity and lower latency for its production line. We will demonstrate how moving IoT applications to the on-premise edge allows the customer to overcome the network bottleneck and quickly improve production performance. We will start with the warehouse branch opening from scratch. The on-premise edge will be provided on demand with SD-WAN, network probe, and the IoT application, while a security SD-WAN gateway will be deployed on the CSP's edge cloud. We will also show the provisioning of an end-to-end service to connect this newly built branch to a cloud-based path. Next, we will demonstrate an upgrade process of the manufacturing branch from LTE to 5G for higher capacity and low latency. Here, by utilizing SD-WAN, we will also present the possibility of implementing the network slicing. Another highlight is that we will introduce the OTT's edge to load the SD-WAN gateway and connect it to the Cloud Interconnect service. In both scenarios, we will show the zero-touch provisioning, the end-to-end orchestration and assurance, and live traffic running from the sensors towards the cloud.
Let's now jump to our first scenario for end-to-end IoT service provisioned across LAN and Wi-Fi equipment, local and public clouds, with end-to-end service tests and live sensor traffic running through this entire network. We start with the digital marketplace, where we have three offers configured for this POC. The first two are for scenario number 1, and the third one is for scenario number 2. We begin by ordering on-prem edge cloud appliance capable of hosting different workload types, such as applications, VNFs, and CNFs. We proceed through the checkout process by specifying equipment quantity, address where the appliance needs to be delivered, and once we submit the order, the equipment is shipped to the site. Underlay connectivity service was provisioned in advance.
When the box is received on-site, just provide the power and connect it to the internet. Just that, and the magic will happen.
Now we are ready to start ordering our end-to-end IoT service over LAN. We select our second IoT video surveillance bundle for LAN, consisting of IoT application, quantity of workload, LAN equipment bundle, WAN-side connectivity option, cloud option, and direct public private cloud interconnect. This small toggle on top instructs service and edge orchestrators to intelligently decide where to put the application among available cloud locations. This decision can be made by orchestrators themselves based on configured application descriptors and several parameters, or in conjunction with analytics module, which takes many other conditions into assumption, such as application type, cloud location capacity, available site bandwidth, and other things. Now we submit the order to service orchestration. Service orchestration accepts the order from the marketplace via LSO Legato interface. It has entire IoT service models in the service catalog. It is centered around IoT applications with various cloud options and connectivity options attached to it in the form of RFS nodes. There are multiple parameters in this model, and some of them are exposed for manual user input, while others are either automatically calculated or fetched from external systems. So in this case, we manually specify SSID name for the wireless LAN, we leave the LAN number blank, we specify pre-shared keys for the wireless LAN access, specify connection name for the flexible interconnection service by entity, and also we specify the pre-shared key for the IoT application itself. After we specified necessary parameters, Service orchestration automatically composes the workflow based on the inputs, various rules configured in the service specification, and systems that require to be provisioned as part of the order. It composes the workflow and defines the tasks and order of these tasks to be executed to have the entire service provisioned. In our case, there are several workflow streams running in parallel, such as on-prem edge cloud provisioning, IoT Central application instantiation, and entity flexible interconnection service deployment. In Adva Ensemble Orchestrator, we can see a network service up and running. It has 3 VNFs: Juniper VSRX for SD-WAN function, Microsoft Azure IoT Edge module for video analytics, and NetRounds IP probe for network testing. VNFs are now ready for further service configuration. Service orchestration now configures Juniper VSRX for on-prem edge cloud applications connectivity. Once Juniper VSRX VNF is up, it goes through zero-touch provisioning process with the CSO, with configuration pushed to it by the orchestration. SD-WAN service will be reviewed in details in scenario number 2, so I don't stop on it now.
MIST site configuration holds the RF templates which define basic RF and MIST AI-driven radio resource management parameters. Here will be the list of access points in your site. Here will be the list of switches and information like missing VLANs learned by MIST. To add security for the IoT wireless LAN, we completely segment each group of IoT devices using multiple passcodes. If an IoT website has a security breach, it won't affect the other devices. The installing technician can use our mobile app to claim an AP or switch via QR or claim code. Our Netcracker orchestration can do this automatically using the claim code for all devices.
When missed APs and switches are received on-site, just provide power and connect it to the on-prem edge. Then, all the devices will be automatically registered with MIST portal and discovered by the orchestration system.
At this point, the switches and APs are configured and running. MIST shows the topology of the switches and their connected wired and wireless clients. Insights gives a detailed overview of the network experience for the entire site, including the switches, APs, wired, and wireless clients.
This is our flexible interconnect portal. An end user can easily establish the connectivity to multiple public clouds on demand, including AWS, Azure, GCP, and Oracle by few clicks. We also introduced a latest service called Microsoft Azure Peering Service to make our FAQ directly connect to the Microsoft backbone. This public peering helps us provide better user experience and stability for PaaS and SaaS, such as O365 and IoT Central. It's also possible to modify the bandwidth on demand by few clicks. As you see, from 10 meg to 1 gig, very easy, isn't it?
We've got our IoT Central application up and running and configured for video analytics use case by using YOLO Video Analytics Each Device Gateway. This gateway has several modules predefined in the device application template, and these modules will be pushed to the IoT Edge application on the on-prem edge cloud once it was provisioned and configured by the orchestration. In parallel, orchestration takes from IoT Central application parameters necessary for IoT Edge module configuration and pushes it there. This includes scope ID, registration ID, and symmetric key for authentication. We can see that IoT Edge virtual machine is now configured, and there are YOLO Gateway modules downloaded here and are running fine. In YOLO on IoT Central app, we can observe each module registered successfully. We can see operating system version, available memory, but currently there are no cameras registered. Now we'll add the camera and put our branch under control with video analytics. We define object detection to be face and person recognition. After some time, we can see there are events registered by the system and can view video streams stored that generated this event, and actually, system recognized the face. The final step for our IoT service instantiation is end-to-end SLA test by Paragon Active Assurance Software Agent, formerly known as NetRounds. Service orchestration triggers test execution via API and supplies IoT app URL and IP addresses to be tested by net rounds. After successful tests, we can observe end-to-end service graph in the orchestration portal and can view various service parameters such as SD-WAN VNF configuration, its IP address, and other things. We can navigate to Service Test tab and download Service Birth Certificate to be shared with the customer, which confirms initial service SLA compliance. If something goes wrong and we start getting alarms, for example from mist, we immediately see it and can navigate to System for detailed troubleshooting.
After the network was up and working, we saw that one of the APs was intermittently going offline. We see in the Mist wireless monitor view that the AP uptime is not meeting service level expectations. Marvis, our AI assistant, will tell us what's wrong with the network. Before I even ask, Marvis tells us that we have pending Marvis actions. Marvis actions tells us the steps to remediate the issue, which is the precursor to the self-driving network. Not surprising, Marvis tells us that the AP is offline and recommends what to check. But what's groundbreaking is that it told us that we have a bad cable between the AP and switch. Once the cable was replaced, the demo was back up and working smoothly.
In our second scenario, we perform upgrade of LTE network with 5G IoT slices stitched with SD-WAN network in multi-cloud environment. This is our initial service graph running LTE VPC VNF. We will replace it with 5G core, deploy a couple more IoT apps, and cover them with IoT slices across SD-WAN network. We order 5G bundle number 3 from the marketplace containing G-Node B, 5G core VNF, SD-WAN, and IoT apps options. We select existing site as location for the service and specify slices to be added here. Also, we include a new network edge cloud for our location as suggested by the system to comply with service SLAs. We double-check added positions and place the order. Orchestration accepts the order and dynamically composes workflow to upgrade the service, add necessary applications, and perform service provisioning. In Adva, we can see connector for our VNFs configured with the necessary for 5G core parameters and VNFs instantiated within the new network service. In Juniper SD-WAN system, we can see our 5G branch up and running now. It has its WAN side provisioned and LAN side stitched with other VNFs as defined by Adva network service. Netcracker service orchestration pushed here firewall and SD-WAN policies for the two IoT slices. In the firewall policy, we've got our IoT traffic sources defined. This comes here from the orchestration, which is aware of 5G network configuration. Firewall rules allow communication for these sources only with IoT central application and prohibit the rest. Breakout profile excludes these addresses, making them reach to the Azure only via internal network config. SD-WAN policy defines how our IoT applications traffic should be handled from QoS perspective. It specifies that for traffic originating on our side, predefined steering profile will be used, which contain SLAs and WAN link failover properties.
As shown in the Azure portal, both VM and IoT Edge service are running now. Let's first look at VM service. We can see VXRX is running well, and we can also check the VM details by just a few clicks. Next, let's take a look at IoT Edge service. Here, we can see all the necessary containers for the AI inference are deployed and in running status.
We've got our second Microsoft Azure IoT Central application instantiated. It will be used for environmental sensors tracking. IoT Edge module for it is provisioned in the Network Edge Cloud this time. On-prem Edge Cloud is used for another video surveillance IoT Edge module. Traffic for this application will utilize SD-WAN and firewall policies configured in Juniper CSO. We specify parameters to be monitored here, which is temperature and pressure. After that, we can see data coming to the dashboard from our branch. NetRounds probe is actively tracking application performance so that we can see in real time how our end-to-end network performs. This concludes our second scenario. We successfully upgraded our branch with 5G network and IoT slices. instantiated and configured several applications in cloud locations, including Azure Stack Edge, and configured them for operation. We also configured SD-WAN network to maintain SLAs for our apps. This is it for today. Thank you very much for watching, and we hope that it was informative for you.